Sun University. I'm very glad to share our research work, GC-Loc, a graphed attention-based framework for collaborative indoor localization using infrastructure-free signals. And my presentation mainly consists of 4 parts. First, introduction. The past decades has witnessed the rapid development of indoor localization techniques, which empowers plenty of indoor location-based services. And in practice, there are many indoor ambient signals are utilized for indoor localization. And among all these signals, geomagnetism attracts much attention recently due to its natural existence, and it is totally infrastructure-free and easy to deploy. However, it is still challenging in practice to realize both accurate and particle geomagnetism-based indoor localization facing this problem. First, spatially decreased signals usually lack of sufficient features, and the temporary consecutive signal sequence may leading to high time or height for sequence collection. And the random environment noise and signal alters also have impact on the localization performance. So we proposed a collaborative indoor localization approach. As we all know, the most common indoor localization scenes are usually some large places with high crowd density, such as shopping mall and passenger station. And the signals collected by multiple nearby smart devices, and their relative relationships usually contains rich location characters and constraints. Employing collaboration and using multi-discrete fingerprints from spatially interconnected sources are able to provide much higher discriminability, meanwhile avoiding the high time responding time and map constraint. So we proposed a graph attention-based collaborative indoor localization framework, which mainly consists of 3 components: collaborative relationship construction, and collaborative localization network design, and finally is location refinement. The first is how do we construct the collaborative relationships, since the distribution of multi-users or devices are not fixed and highly dynamic. So we utilize the graph structure to construct an adaptive graph representation in which the vertices indicate the decreased signal fingerprints, and the edge denotes the distance between the corresponding 2 vertices. The construct representation is not applicable to the collaboration in the indoor sense with multi-users, but also works well with multi-time-step collaboration for single-user sense. Then for network design, intuitively we consider employing state-of-art graph learning techniques to achieve the aggregation of features. And for indoor localization, the propagation or distribution of localization signals are usually fixed unless the indoor environment changes. So therefore, in a specific indoor sense, although the location of users and their collaboration and their relationships are highly dynamic, but the signal fingerprint collect at a specific position, and the corresponding in relationships are usually static. That means users' location and their collaborative relationships are static at a specific time step of the dynamic variation. Although graph learning is originally suitable for the problem that nose and eyes are relatively static, it can also work for dynamic indoor localization at a static point in time. And considering the existence of random noise and signal authors in practice, we employ ensemble learning and devise a signal similarity-based model fusion strategy for multimodal joint localization estimation. To be specific, we first train multiple independent localization models with different inertial settings. Then we backward consider the signal fingerprint matched with models prediction in geotagged signal database, and based on which we further calculate the signal similarity as adaptive weight for the ensemble model fusion, and thus achieving location refinement. Through the model consensus, the proposed approach can overcome the problem that individuals' models is prone to random error and further improve the robustness. So for experiments, we have conducted extensive experiments in 3 trial sites, including an office-area, a spacious hall, and a whole floor of lab building. And the results demonstrate that in all these 3 trial sites, the proposed approach outperforms competing methods by a wide margin, reducing average localization error by more than 42%. And more detailed experiment results can refer to our paper. Finally, the conclusion. In summary, we proposed an efficient collaborative indoor localization framework which can be easily extended or incorporated. And in the approach, we first construct an adaptive graph representation for collaborative relationships. Then we devised a GT-based collaborative indoor localization network. And finally, we designed a location refinement strategy with model consensus. And the experimental results demonstrate the effectiveness of our approach. And for future work, we will further explore about device celebration through crowdsourcing, and we also will considering the data security and privacy protection during the collaborative localization. So this is all of my presentation. Thank you.
Up. Are there any questions?